Welcome to today's Explainer. I am absolutely thrilled to guide you through this one because we're going on a seriously fascinating journey. We're going to start right down at the micro level of mixtures. You know, those invisible combinations of matter that make up pretty much everything around us, and we'll scale all the way up to see the massive macro level impacts they have on our daily lives. Okay, let's dive in.
Have you ever actually stopped to wonder how we get those perfectly uniform sweet white sugar crystals from a massive, tough, green sugar cane plant? Or think about something even more critical. How can a doctor pinpoint a microscopic disease like malaria using just a tiny drop of blood? At first glance, these everyday mysteries seem completely unrelated, right? But they're actually made possible by the exact same fundamental science, the science of separating mixtures. Separation techniques aren't just tucked away in laboratories. They are absolutely everywhere in your daily life.
So here is our roadmap for today. 1. The world of mixtures. 2. Measuring solution concentration. 3. The science of solubility. 4. Separation through crystallization. And finally, 5. Distillation and real applications. Let's get to it. Starting off with Section 1, the world of mixtures. Let's understand the basics. Okay, so the absolute most crucial thing here is understanding the hard line between the two main types of mixtures. On one side, we've got homogeneous mixtures. The magic keyword here is uniform. If you thoroughly stir sugar into water, every single sip is exactly as sweet as the last one. It has a uniform composition throughout, which we also call a solution. Now on the flip side, we have heterogeneous mixtures. Think about stirring a handful of sand into a glass of water. It's totally non-uniform. The sand particles are totally visible, and if you just leave the glass alone for a minute, they'll all settle right to the bottom. So uniformity is literally the ultimate differentiator here.
Seeing this side by side really hammers the concept home. A beaker with a perfectly clear, well-mixed liquid is your classic homogeneous solution. Your eyes just can't pick out the individual parts because they're perfectly distributed. But a muddy, heterogeneous mixture, you can physically see the separation happening, with all those heavy particles gathered at the bottom. But here's the thing. Scientists don't just rely on the naked eye to tell these apart. They actually use light.
Let's see how this works in an actual scientific observation. Imagine shining a bright red laser pointer straight through a beaker of salt and water. What happens inside the glass? Well, absolutely nothing. The liquid looks completely dark where the laser should be. Why? Because a homogeneous mixture is a true solution. The dissolved particles are so incredibly tiny that the light passes right through them completely invisibly, and it only shows up as a dot on the wall behind the glass.
Now compare that to a heterogeneous mixture of chalk powder and water. If you shine that same laser, you get this intense, glowing red beam cutting right through the liquid. Because those chalk particles are large and just kind of floating around suspended in the water, they act like millions of tiny mirrors. They violently scatter the laser light in all directions, which creates that highly visible beam. It's a beautifully simple, instant test for uniformity.
But here's where things get really interesting. Take a mixture of just a few drops of milk mixed with water. To our everyday eye, a glass of milk looks completely uniform, right? But if you hit it with the laser, the beam is clearly visible passing through the liquid. This visually proves that milk, which is super surprising to some people, is not a perfectly uniform solution at all. It actually contains suspended fat and protein particles that are large enough to scatter that light. So it's actually a heterogeneous mixture. Crazy, right? Moving right along to Section 2, measuring solution concentration. This is where we start quantifying these mixtures.
So, concentration. It's defined as this specific amount of solute, that's the stuff being dissolved, present in a given amount of solvent or solution. And let me tell you, getting this right isn't just some boring lab exercise, it is literally a matter of life and death. Think about Dr. Dilip Mahalanobis, the brilliant Indian pediatrician who developed the oral rehydration solution, or ORS. ORS isn't just any random sweet, salty water. It requires a highly specific concentration of salt and sugar to safely rehydrate a body suffering from severe diseases like cholera. In situations like that, precise ratios mean absolutely everything. So how do we actually express that precise ratio? Here's our first mathematical formula: mass by mass percentage, or percent M by M. It's simple. You take the mass of your solute, divide it by the total mass of the entire solution, and then multiply by 100. It basically tells us exactly how many grams of solute are hiding in 100 grams of the total mixture. Stay with me here, because I'm going to show you exactly where this is used in your own home right now. Take a standard nutritional label on a packet of milk powder, the kind you'd find in any supermarket. Believe it or not, this label uses the exact mass-by-mass logic we just talked about. Milk powder is a heterogeneous mixture, and the label breaks down its composition. 26 grams of fat, 49 grams of sugar, and all of that is calculated per 100 grams of the powder. So every single time you read a food label to check your salt or protein intake, you are literally looking at mass-by-mass concentration in action.
Now, let's look at the second major way we measure this stuff, mass by volume percentage. This is the mass of the solute divided by the volume of the solution times 100. Why do we even need this second formula? Well, practically speaking, when you're dealing with liquids, especially in medicine and laboratories, it is just so much easier to measure the volume in milliliters than it is to carefully weigh it out on a scale.
And this brings the math immediately back to the real world. Think about a standard 5% glucose intravenous infusion bottle. That 5% means there are exactly 5 grams of glucose in every 100 milliliters of the solution. Or consider a standard hospital saline drip. Those are carefully calibrated at exactly 0.9% mass by volume of sodium chloride. That 0.9% concentration is strictly calculated to safely replace body fluids without damaging your blood cells. A little too much or a little too little, and the solution actually becomes dangerous.
All right, let's jump into Section 3, the science of solubility, and specifically, the role of temperature. I want you to take a quick second and guess something for me. How do you think temperature affects solubility? Like, if you heat up a liquid, can you dissolve more solid into it? And what about a gas? The answer is absolutely fascinating. Generally, heat makes solids dissolve much more easily. Think about how much faster sugar dissolves in hot tea compared to iced tea, right? But for gases, the exact opposite is true. An increase in temperature actually makes gases dissolve less in a liquid. And this little temperature trick is actually one of the main properties scientists use to pull mixtures apart.
Which leads us perfectly into Section 4, separation through crystallization. Let's talk about separating solids.
So here's how we break down the complex laboratory purification process known as crystallization into 4 super accessible steps. Step 1, you heat up your liquid and add your solute. Let's say we're trying to extract pure copper sulfate, and you keep adding it until no more can possibly dissolve. You've now made a hot, saturated solution. Step 2, you filter it while it's still hot just to remove any basic physical impurities. Step 3 is where the real magic happens. You allow the solution to cool slowly and completely undisturbed. Remember how we just said solids are less soluble when it's cold? Well, as that liquid cools down, it literally can't hold all that copper sulfate anymore. So the pure solid is forced out of the solution, arranging itself into beautiful, regular geometric patterns, crystals. And finally, step 4, you just filter out those brand new crystals, give them a rinse, and dry them. Just by carefully managing the temperature, you've extracted a highly pure substance. It's like a magic trick, but it's just chemistry.
And finally, Section 5, distillation and real applications. Let's look at some real-world uses.
So what happens when you need to pull apart 2 completely mixed liquids? To solve this, scientists use distillation. The elegance of this technique is just brilliant. It relies on the simple fact that different liquids boil at different temperatures. Boiling points are basically the secret keys to unlocking mixed liquids. For example, if you have a completely homogeneous mixture of acetone and water, you just heat the flask. The acetone boils and turns to vapor at a much lower temperature than the water does. So you capture that acetone vapor, run it through a cooling tube to condense it back into a liquid, and collect it in a totally new flask. The water just gets left behind in the original flask. Boom! You've just cleanly separated 2 perfectly mixed liquids.
But hey, distillation isn't just about harsh laboratory chemicals. It actually has incredibly rich cultural applications. Take the town of Kannauj in Uttar Pradesh, India. They use an ancient, beautifully poetic distillation tradition known as the Deg Bapka method. They take the raw materials of the earth and use the hard science of boiling points and condensation to extract and capture the exact, distinct scent of the first rain hitting dry soil. They turn that into a world-renowned natural perfume called Miti Ke Itar. It is quite literally high-level chemistry being used as a pure art form.
And that wraps up today's explainer. But before you go, I want to leave you with a bit of a challenge. Take a second and just look around the room you're in right now. Based on everything we just learned about mixtures, concentration, crystallization, and distillation, what everyday items surrounding you were created using these exact separation techniques? Is it the salt in your kitchen? That bottle of perfume on your shelf? Maybe the medicine in your cabinet? The chemistry of separation is hiding in plain sight everywhere you look, and now you've got the tools to actually see it. Thanks so much for joining me today.